Okay, perfect. Sorry for the delay. So, first, what I would like to do today, I added a lecture here, and it's still not in IOL. I explain you why, which is on decision theory. I mentioned to you last week that I was thinking about the opportunity to say something more about decision theory. Indeed, during this week, I decided to dedicate some time on it because it is becoming extremely important in the context of sustainability, and for some reason it is not ignored, but sometimes, especially from the point of view of engineering, it's not considered enough. Usually policymakers and also engineers and the stakeholders, in the presence of alternatives to ensure sustainability, they still decide on a heuristic basis. Heuristic means basing on experience, basing on discussion, without a formal and analytical approach to the problem. What is the problem? Is to evaluate among different alternatives what is the most appropriate to get to target. There are indeed analytical approaches to support decisions, as you may know, and we introduced also an exercise on pairwise comparison that gives to you an example. But as I said, often these analytical approaches are not taken into account, are not considered, because as I said, people prefer to base the discussion on personal experience, personal belief. There is also a reason on that. If you base the discussion on your opinion, there is more flexibility. You have an opportunity to better support what is your preferred target, because you can claim that you know things, but you don't have to prove them. Instead, if you adopt an analytic approach is less prone to flexibility. It's something that is based on a rigorous evaluation of costs and benefits, and therefore it leaves not much space to flexibility. And this is why people sometimes they try to decline the opportunity of using analytical decisions. But this field is now rapidly evolving just because in the presence of urgent problems involving sustainability, it's not clear what is the most appropriate way forward. And therefore, there is a lot of research that is now dedicated to decision theory, which evolved a lot with contribution continuously proposed by the literature. But as I said, the literature on engineering, the literature on climate science, and the literature on decision theory, sometimes they don't interact with each other in an effective way. So this is why I decided during this week to make an effort to try to read recent contributions in order to give to you an overview. But on the other hand, I don't want to ask any question at the exam on decision theory, because it's something that I am introducing to you just the last day. It's like a final seminar, but I don't want to make you uncomfortable to begin a new topic just the last day. And this applies not only to the first exam, but also later on for this year. I will not ask anything about decision theory, with the exception of what we did last time, pairwise comparison. So something on pairwise comparison. And I want, as I said, to reserve a part of the last hour today to make examples of questions that I may ask to you. I want to be extremely clear. But on the other hand, I want to be very clear from now that what I'm talking to you about today is not a topic for the exam. And this is why I didn't include this lecture in IOL, because I want to be clear on that. So I am putting this lecture here because I think it is a useful information for you, otherwise I wouldn't teach about it. On the other hand, it's not in IOL for this reason. Okay, so let's open this page, which is new. It was published yesterday, and I prepared also a PPT, so let me download also the PPT, because it's easier to follow on the PPT. Okay, so should work. Okay, good. So this is a lecture on decision making with explicit reference on water resources management. When we talk about decision making in water resources management, climate change automatically gets involved, because in the context of sustainability, as we know, climate change is playing a topical role. It's a fundamental issue. This doesn't mean that it's a priority. It just means the fact that today, if you get involved in a discussion about sustainable solutions for water resources management, you cannot ignore climate change. It doesn't matter if you believe in it or not. It doesn't matter if you believe that climate change is the first priority or not. The result of the situation is that anyway, we cannot ignore it. And the result of this is that much of the literature about decision making in water resources management refers to problems posed by climate change. I tried in this lecture to be very general and to make the fewer references to climate change that was possible to make. So I tried to reduce them a lot. On the other hand, there are some examples proposed by the literature which are about climate change, which I think are relevant. So in some of the slides you will see reference to climate change. Don't think that it's the only problem. It's just the fact that some methods that I am talking to you about today were just conceived by thinking of climate change. So I cannot avoid a reference to it, but try to keep a broad vision. Okay. That being said, let me make a premise. So what is decision theory? Decision theory is something that should support you to take a decision. It's a topic that may look like boring, may look not interesting, may look a bit obscure, like statistics. It's not like that. It's a topic that deals with everyday issues. It's a topic that tries to introduce rigor in solving a problem that it's part of our everyday life. Taking decisions, we take decisions every day. And very often these decisions are affected by uncertainty. The boundary conditions, the input data are uncertain. Like, should I take an umbrella today or not? Or like, should I take the bus rather than the car, rather than the train to get to my working place? There are uncertainties because you don't know if there will be traffic, you don't know if the train will be late, etc. And in our everyday life, we are used to deal with these decisions, which are part of our being humans, of the fact that we have the capability to evaluate the pros and cons, costs and benefits of alternative solutions. Very often we base our decision on just heuristic methods. Heuristic means, as I said, based on your experience, your preference, and in most of the cases, when you are asked, when you take a decision for yourself, heuristic methods are the most appropriate, meaning that they are quicker. Sometimes we need to take decisions in 1 fraction of a second, like 1/10 of a second, like when you drive. And of course, you cannot take your computer and make use of an analytical method. So in most of the cases, again, the heuristic solution is the most appropriate. And also, let me say that when we make use of our experience, when we make use of our intuition, and this is unbiased, and we have a good experience, a good intuition, this is by far the most proper way of taking decisions. So our personal knowledge should never be ignored. There are some factors, some issues that play fundamental role in decisions that cannot be quantified. Also, think about your personal belief. which may be indeed very appropriate. And the message that I would like to convey is I'm teaching about analytic approach, which doesn't mean that heuristic approaches are useless. They are by far the preferred option. When do we need to introduce rules? We need to introduce rules when we have to seek an agreement between subjects that have different opinions. So, when you have to discuss about taking a decision and with a person, take the example of a discussion between two people, and they have different opinions, usually the usual way, heuristic way that we adopt is just to talk. To talk, make a confrontation, to try to agree. Sometimes this is impossible. When it becomes impossible, what do? We go to a lawyer and ask the lawyer to help us in reaching an agreement. And the lawyer makes reference to rules. Rules have the advantage of being transparent. The law is a rule. They are transparent, they are objective, and therefore the lawyer just looks at the rules and takes the decision by following an analytic procedure, because he just follows the rules. When you introduce rules, there is a limitation to flexibility, and therefore, let's say that when you can avoid to make reference to rules and to use your, in Italian we say good sense, it means good feeling, good intuition, provided this intuition is indeed good, it's still the most preferred solution, because it's flexible. It allows you to take into account external inputs that are not quantifiable in numbers. On the other hand, when the good feeling, the good experience is lacking, we need to refer to rules. So, the concept is, not necessarily you need to adopt a rigorously based decision method, but when you get involved in a discussion and reaching an agreement is difficult, because you feel that some people are biased, some people are not transparent, then it's definitely the case to adopt a decision support system structured in an analytic way. The advantage with rules, and the decision support system is a rule, is that you agree first on the rules. How should we take this decision? What should we take into account? Economic benefit. Perfect. Let's take into account the economic benefit. You fix the rules first, and then you make your rigorous evaluation of the conformity of alternatives to the rule. This is an advantage because you split the decision in two parts. A first part where you don't see, you just fix the rules without knowing what is the effect of the rules on the outcome, and the second part where you apply the rules. It's like we do in our institutional setting. We set the laws without making an explicit reference to a case. When one sets laws, shouldn't make explicit reference to a case. Otherwise, the law becomes ad personam. So we set the law in our institutional agreement, and then later on, once the laws are approved by the government, we apply them. Okay, so first let me say that decisions were taken by humans since the prehistory. And look, for instance, at the Egyptians. This is a picture of the Nilometer. The Nilometer was an instrument that measured the level of the Nile River. They went with this kind of well deep in the ground, and with this stuff here, they measured the level of the Nile River. Why did they need to know the level of the Nile River? Because you know that ancient Egyptians were mainly basing their economy on agriculture, and agriculture dependent on the fertilization that the floods of the Nile River brought to their fields. So they knew that when the Nile River was quite high in spring, there would be a good crop season. And so they used the Nilometer to predict, to take their decisions on cropping techniques every year. And this is an interesting example. Take into account that they went on for about 600 years to monitor the Nile River levels, and this is one of the few hydrometric series that we have in the far past. Unfortunately, they collapsed and they stopped the measurements. Okay. And when decision theory became a science, essentially, let me say that probability was created for supporting decisions. So one may say that the birth of probability may be adopted as the birth of decision theory. The birth of probability, it's about 1700. You can locate between 1700 and Bernoulli worked during the 1700s. And therefore we can say that we can locate at around 1700 the time when people first needed to get some support to their decisions. Probability was born essentially to support gambling. At the beginning, they wanted to support gambling, but gambling is a good example of an activity that requires quick decisions, and it's a good example of an activity where decisions are extremely important. But if we consider decision theory in the modern sense, like analytic methods for taking decisions, then we can say that it was born about 100 years ago, 1930, 1940, when people invented the simplex algorithm. What is the simplex algorithm? Is a linear method for identifying the optimum of an objective function. Okay, so it's just an algorithm, one of these algorithms that we are using today in R when we call optim. It is not using the simplex, but it is using a similar algorithm. Simplex was linear. Linear meaning that a linear approximation of the objective function was adopted. And given that objective functions in hydrology often are nonlinear, nonlinear means that if you have a parameter to optimize, the objective function is not a linear function of the parameter. We know that it's quadratic, for instance. Sum of squares is quadratic. Simplex adopted a linear approximation, and this was the linear approximation theory was widely used since then, since 1940 up to 1990 in water resources management. If you look at a classical book of water resources management, Laux, published in 1981, half of the book is on linear methods for identifying the optimum. If we go back to what we did so far, we talked about rainfall runoff models, and we talked about parametrization, calibration, optimization. And we said you can go with a trial and error, or you can use automatic optimization. Perfect. This kind of first methods for decision theory were meant to support automatic optimization. And then, about around 1990, people started to make research on more efficient methods for searching for the optimum. And there was a lot of research activity carried out mainly in water resources, not mainly, but a large part of it in water resources management that led to the development of the software that we are using today. But this is just optimization. And the classical literature, I want to stress it again, on water resources management focuses on decision theory intended as optimization. But then Yeah. Then, since 1990, therefore less than 30 years ago, up to today, there was an increasing awareness of the importance of uncertainty in water resources management. This increasing awareness of uncertainty was also induced by the fact that people realized, and you may think, why so late, but think that water resources management was born in 1970. People realized that their predictions were contradicted by unexpected events, like unexpected floods, unexpected droughts, and some people started around 1990 to relate these unexpected events to raising temperature at the global level, and so they started talking about climate change. Climate change became an issue around 1990, and up to 2000 it was not a urgent issue, it was not considered a urgent issue. The result of that, unexpected events, doubts about climate change, was that people became increasingly aware of uncertainty. Take into account that so far, when we talk about our models, and we talked about parameter estimation, we didn't say anything about uncertainty. Like, we use a measured rainfall series to calibrate a model, and a measured series of river flows. But they are for sure uncertain, and if they are uncertain, we left open the question, what is the impact of such uncertainty on parameter estimation? What is the impact of such uncertainty on predictions? And therefore, an intensive research activity started, 2000, on the impact of uncertainty on decisions. So people wondered, what is the best decision to be taken if I know that my information is uncertain? Is it still to look for the optimum? Maybe not, because if we take our rainfall series and our river flow series and we select the optimum, but in the future a different rainfall may come, and the optimum that I observed into the past will still be the optimum in a different future? For sure not. So we could think of studying several optimums. We could admit that rainfall is uncertain and say, okay, let's take this rainfall, the optimum is here. Let's take another rainfall by perturbing what I observed. And what is the optimum? Is still close or it's very far? And in terms of effect of the decision, is my decision regrettable? Is my optimum regrettable if climate changes? Some decisions may be highly regrettable if there are changes. Some others maybe not. So you may prefer a decision that is not regrettable instead of the optimum. These were the questions that people wondered, like, how should I decide then? Just looking for the optimum, maybe not the best solution. For sure, when you work with sustainability, it's not a good idea to just look at the optimum. Because, of course, it depends on how you define the optimum. Optimum of benefit, optimum of environmental preservation. But in any case, you should look also at no-regret solutions, because they are for sure more sustainable. And it's a completely different story. No regret from optimum. If you think about investing your money, you look at the optimum is risky. In economy, the optimum, max benefit, is risky. So you need to buy some, I don't know how to say in English, probably titles, some values in investments that are at risk. And they, if they are successful, they give you the max benefit. But usually when you invest your money, you don't just look at the max benefit, maybe risky, you also want to minimize the risk. So when you invest the money, usually your advisor says, what is the level of risk that you are tolerating? This means that she is willing to look at the no-regret side of your decision. So it is a science that developed, as I said, recently. And the solution was, let's seek for a decision that is robust. And therefore there was another term that arose, which is robust decision. What does it mean, robust? It means that in the presence of uncertainty, of course, when I talk about robust decision, I am in the presence of uncertainty. If you don't have uncertainty, just look for the optimum, of course. If you don't have uncertainty, just look for the optimum, according to an assigned criteria. But if you have uncertainty, an interest arose for robust decision. What does it mean, robust? It means that it's never completely wrong. It's not necessarily optimal, but whatever your condition, whatever your future will be, a robust decision will not be a disaster. So the criteria is to avoid the disaster rather than looking for the optimum. And this is the reasoning that, as I said, you make when you invest money. Your first priority is to avoid bankrupt. And then you look for what is the best condition that, in any case, avoids bankrupt. This is a robust decision. And therefore, people started developing methods. And this is what I want to talk to you today. And pairwise comparison is part of that. And this lecture proposes a brief review. And let me say, first of all, that it's not exhaustive. There are several methods for supporting decisions. I am focusing on robust decision methods. And I am listing just a few of them, because you may also make several variants of these methods. And I identified what are the methods that the literature think are reference terms. And I would like to start with this first method, which is called InfoGap decision method. It's a robust decision method. First of all, why it's called InfoGap? Because InfoGap means a gap in the information. Means that there is a mismatch between what is known and what needs to be known. So there is uncertainty, basically. And therefore, this is the reason for the name. A method that takes into account a gap in the information. What is the concept here? And let me make an example. Let's suppose that you have to estimate a parameter for a model. And you look for the optimum, that's fine. And you get what we got, optimal parameter vector for I0, for instance. InfoGap aims to check what happens if the parameter is wrong. So let's suppose that you have your parameter A. A is the optimum. And let's suppose that you admit that instead of having a single value for the parameter, you allow your parameter to vary into a range. Let me put here alpha, not b, in order to make a difference. Alpha is a quantifier of uncertainty. And then you look, you try to apply your model within this range and see what happens on the decision. Is still the decision reaching your target or not? Of course, what will happen is that if you keep alpha small, any value within this range will anyway imply that the decision gets the target. But if you increase alpha, you will get to a certain point where the decision is regrettable. It's not getting to target. So InfoGap varies alpha to determine what is the max level of uncertainty that still gives rise to a good decision. This is the concept. Of course, here I made the example of a parameter for a model, but this could be also an input variable. It could be, like for instance, a range of variability on observed rainfall. So instead of using just one rainfall series, you randomly generate another rainfall series by perturbing, for instance, each observation plus minus something. And then you see what is the effect on your decision on that. And then you determine the max range. InfoGap has a distinguishing behavior. So far, basically, it is clear what it does, which means that you can assess what's the max level of uncertainty that you can tolerate. And therefore, you compare this max level of uncertainty with what you feel may be the uncertainty of your situation. If you see that alpha is very large compared to your perception of what could be the level of uncertainty in your measurements, in your parameter, then you may say, okay, this decision is fine. But if, according to your perception, you realize that uncertainty may be higher, then you may change your decision. Keep in mind that in some lucky cases, uncertainty could be quantified in probabilistic terms, and therefore you may be able to compare your alpha with the max acceptable level given by probability theory. As I said, InfoGap has another distinguishing behavior, which is, it may happen that by varying your parameter A within the range, you get an outcome that is better than expected, better than the optimum. This is called unexpected windfall or opportunism, which means that uncertainty may also be an opportunity. This is something, for instance, that in climate change, I don't understand why it's not considered. So in climate change, we assess the negative implications of climate change, but there are also positive implications, which are clear. There is no need to discuss them. Of course, we feel more comfortable. We didn't feel comfortable in May, and the agriculture didn't feel comfortable. So on the one hand, we say we need water, we need rain, but if you get too much of it, it's a problem. So if indeed we have global warming ends up with less rain, there are opportunities. And these are usually discarded. InfoGap doesn't discard them. InfoGap says, okay, let me check what is the outcome, also in terms of opportunism. And then, depending on the level of uncertainty, InfoGap develops curves. Everything is explained here. Curves of regret versus alpha, opportunism versus alpha. And then, when you have clear what are the consequences of uncertainty, you may be able to assess what is unexpected and positive, negative and positive outcomes, what they are, and you may be able to compare, related to uncertainty, what is the effect of the decision. So the final aim is, let me see what happens to my decision in the presence of different level of uncertainty. It's quite easy to do. If you have a model, you just have to, you have a model of your system and you have a model of the benefit, so you have an objective function. It's quite easy to change parameters and to evaluate this max range alpha that you can tolerate. There are softwares for doing that. We don't need to go into the details. I may write the same thing by using a mathematical formulation. There are references in my webpage that you can look at. Most of them are available on the web. So there are, you will see analytic interpretation. We don't need to understand that. We just need to grasp the concept. Okay. This is what I already mentioned. You see, I said that there is a robustness function. The robustness function shows to you the max range that can be tolerated while ensuring a given minimum reward for each decision. And there is an opportuneness function, the minimum range required to enable an unassigned maximum reward windfall for each decision strategy. Do you know what windfall means? It's like, in Italian we would say manna, and it means an unexpected benefit. So the user may decide to minimize the worst case outcome or maximize the best case windfall. This is also a possibility. When ensuring sustainability, you may decide to minimize the regret or maximize the unexpected windfall. Sometimes you may be able to tolerate some regret if it is compensated by a greater probability of unexpected windfall. This is a unique feature of InfoGap. I didn't find in the other methods an emphasis on unexpected outcome that may derive from uncertainty. I think it is important. I think it is important also to consider this case. Other methods consider it implicit.